Hello everyone, today I'll be sharing my findings on this week's homework. Before I start, I would like to share that I will not be talking about question 1, question 4, and question 5 as they were written answers, and if you would like to learn about them, you would have to read the IPython notebook. So let's start with question 2. On question 2, we have a bunch of bounding boxes, a bunch of detections, and we're supposed to use the non-maximal suppression method in order to find the best bounding box. So this is the given image with a bunch of bounding boxes. Out of these, we use the non-maximal suppression method, and we find the best bounding box out of the bunch. So essentially, my finding is that this is the best according to the NMS. There's another question: can you backpropagate through NMS? The answer to that is yes, but I couldn't find a way to code this. I think at my level, this problem far exceeds my level. So I'm moving on. So I will just be going through question 3 really briefly. The reason why is that it's you should actually be reading the notebook if you would like to learn about them. But for your reference, I'll be sharing my results. 64 times 21 is the answer, and that's what I found out. I'm moving on to question 2. On question 2, like not question 2, but part 2 of question 3, we're supposed to find calculate the same tensor using different ways. So part 2 and 3 aims to tries to find the same tensor using different ways. I'll not be going in depth. So 4 by 256 times 3 by 3 times 3, that's the same result. I'm moving on to the other parts, and I will be zooming in this time because I will not be sharing my answers for question 4. You'll have to go ahead and read those parts if you'd like to learn about them. So let me actually zoom in one last time. All right, 300%. Let's see. Okay. Oh, this sent us all the way back to question 8. Let me just fix that. All right, so that's basically it. Cool. I'm not sharing any of the results this time. So the answer is supposed to be 4 times 256 times 3 by 3, because essentially what we're doing is on part 2 and part 3, we're trying to calculate the same tensor in different ways. So let me just move on. I'm passing question 4 and question 5, so we're directly on question 6 this time. So on question 6, we're doing some regression based loss. We're trying to estimate the bounding boxes. I think question 6 was the hardest question because I had a hard time trying to find the definition of normalized coordinates. Essentially, what normalized coordinate, like you have to know when we use normalized coordinates. We use them when we use the anchor box, right? So I actually read the paper on YOLO, and what they do is they divide images into different anchors, and they have a region of interest where they check if the object is detected or not. And the way they do it is that by comparing the normalized coordinates. So I'm hoping that this gave you some idea. I also pulled up the paper which helped me understand what those normalized coordinates are. This is the name of the paper. And oops, so I accidentally closed it, I think. Let me just download it again really quickly. But essentially in there, there's an image. Let me actually show you the screenshot of that image really quickly. Oh, it downloaded. before I, okay, so this is the screenshot. So what's an anchor was my second question, and that's how I learned about it. Its geometric meaning. Essentially, that's what an anchor is. The geometry of an anchor, predicted bounding box, and the ground truth box. All right. So how do I show the answers for this? Like, how do I should prove the? Oh, okay. So let me just zoom in a little bit, and then I will. Okay, 250%. All right, let's just go. Okay. Oh, again, then this sent me to question 8. So I can't zoom in this much. 200% is the maximum amount of zoom. All right, so question 6. All right, so this was the loss I found from the first part, and then the second part actually asks us to implement this. So our center of the current predicted the bounding box, I is the anchor. I embedded the paper inside this notebook so that you can understand what that is. There's a written answer just below it, below the next part, but I will still be, I think if you do not know if you do not show those previous results, like using like you can't compare them. So essentially, L2 loss is more sensitive to outliers and has a larger scale than L1 loss. Normalization helps in removing the geometrical differences between the ground truth and predicted boxes. The log transform helps in removing scale bias to prevent prioritizing large objects to small objects. Essentially, those were my findings. I mean, those were my findings from comparing them. There is a bonus part which actually asks us implement smooth L1 and calculate the loss again. What does smooth L1 bring to the table? How it is different than L1 and L2? Provide your answers to the markdown cell below. So what that part is essentially, so we are trying to estimate the bounding boxes on L1 and L2, and the smooth version of this puts the best parts from L1 and L2 on the same part. Again, I implemented that. I will not be showing you the code, but I will share the number. Okay, so smooth L1 loss is 9.4. All right, I will also read this part. We can see that smooth loss is similar to scale L1 and it's not sensitive to outliers, but due to the square term of minor errors, it cares less about smaller mistakes. Like, I think you can just read these parts, so I will not be sharing more. Question 7. All right, so question 7 is important because now we're starting to talk about classification loss. We have binary classification. So in binary classification, we are asking if something is there or not. And the issue is, it's a really simple method, but then I should actually be showing these. So okay, so these are my answers for question 7. I will not be sharing any code. So simple detection. So we are doing some really simple detection here, right? So we are asking if there is an object, if there is something, or if there is not. We aren't even doing the cat-dog deal here, because in the cat-dog deal, it's a triple. Like there are three possible outcomes. It can be a cat, it can be a dog, or it can be nothing. So in that sense, this is more of a easier thing. So the case with this binary classification is that what if the data set is unbalanced, right? So this causes the imbalanced classification problem. We use, so throughout the homework, you will see that we use focal loss in order to solve this imbalanced classification and detection problem. And here are the results. And here's how to read these results. So 8.2 to the power of, so it's like 8.2, right? It's above 1. That's considerably higher than all of the other findings. So we can say that we have found the first value is much higher than the other values. So we only say that we have detected something if there is a significant difference between between the samples, and we can say that, for example, I found out something on 8.2, right? Here we can see that negative cases are rare, but since their weights are large, 4 compared to 1, its loss term is quite large, making the model prioritize it. So again, this time I am moving on to question 8. And on question 8, I will only be showing the part where I have the graph, because the rest of it is written parts again. So far, all of the written parts I have shared are like, if you can't write the code, then you can't obtain the results. So it means that like you do not have a basis. So I'm hoping that this won't cause any problems. So yeah, on question 8, we have a precision recall curve, right? And these are ranked in the order of their scores. 1 means that we have a true detection, 0 means that we have a false detection. What we are doing with precision recall is we're trying to, so I have some notes because the homework was long this time. I had to prepare some notes. We are doing it to, we are ranking our predictions in terms of their scores. So the reason why we see that like this slope here, that converging slope, is that we are ranking our precisions, right? So we rank it because we rank it because we want to see obtain this exact result that I will just say. So if I am willing to have 40% recall, then I have 100% precision, right? And the objective here is that 40%, at least for 40% of the time, we will know that we are 100% correct. I mean, so this actually sounded to me like a really, really bad accuracy, because, you know, like someone is showing you 100 samples and you're only telling them that 40 of those 100 samples are what you're looking for, and the case is that like you are 100% sure that 40% is 100, like is what you look for, but you're missing out a lot, is what I'm trying to say. So I think I have to improve on how to read these things. So all of my predictions are correct. This means that I'm missing 60% of the true positives. Like, isn't that true, or am I incorrect here? Yeah. So that's my take on question 8. So thanks a lot for listening to me.